Exponential growth and decay scenarios often involve a lot of changing of forms. So if I have an exponential scenario, like a to the power of x is equal to y, if I want to solve for x, I need to be able to switch this into logarithmic form. So I need to be able to move that base over to the right-hand side, making it a logarithmic expression with base a of y, the argument, and then dropping down that power. If I take a look at this first scenario, 15, it says that a machine was purchased for $10,000, and we have a function that determines its value in t years. This function here, v is equal to 10,000 times e to the power of negative 0.3t. Okay, that initial principal amount, the initial value is 10,000. I can see it's decaying because this growth constant k is negative. And t, again, is going to be in years. The problem then tells me that the machine must be replaced at the end of the year in which its value drops below 1,500. So we want to know how long is that going to take and how many years will the machine need to be replaced. So I want to know the time when that value hits 1,500. So solving for t here. Setting up my equation, the value I'm interested in is 1,500. I have the initial value 10,000 times e to the negative 0.3t. Now to solve for t, I first need to divide both sides by 10,000. I can take out some common factors from that left-hand side, simplifying that fraction. It's going to simplify down to 3 over 20. I'm left with e to the power of negative 0.3t on the right-hand side. Here's where we're going to have to switch it into log form. I'm going to take that base of e and move it over to the other side, changing it from an exponent into a logarithm. Log base e of 3/20 is equal to negative 0.3t. Okay. I'm going to rewrite log base e as the natural log. I'm also going to divide both sides by negative 0.3. Without a calculator, or if we wanted to leave our answer in exact form, we would have to leave it in natural log form. Natural log of 3 over 20 divided by negative 0.3. This would be an acceptable answer since it is exact. If you converted that to a decimal, it's going to be about 6.32, so it would need to be replaced at the end of the 6th year. Now on to number 16. It says a strain of bacteria growing in a pond doubles every 5 minutes. So every 5 minutes there's twice as many bacteria as 5 minutes before. So it says, assuming you start with only one bacterium, we want to know how many bacteria would be present at the end of 96 minutes. So my time here is not years, my time is going to be in minutes. Now I have the formula for the amount of bacterium is equal to A naught. That's going to be my initial amount, which it tells us we're starting with one bacterium, times E raised to the power of K times T. And K, again, is your rate of change. This is our growth rate. We do not know that. So we're going to solve for that first. What we do know is one other piece of data, that every 5 minutes, the amount of bacterium is doubling. So when T is 5, we're going to double from 1 bacterium to 2. Plugging in what I know, I have 2 is equal to A naught, which is 1, times e to the power of k times t, which is 5. And now I can use this to solve for that growth rate. Dividing both sides by 1 is just going to leave me with a 2. So I have 2 is equal to e to the power of 5k. Switching into log form is going to allow me to drop down that power of 5k. I'm left with the natural log of 2 on the left-hand side. Divide both sides by 5. We get k is 1/5 times the natural log of 2, which means my function here is 1, which is A naught, times e to the power of 1/5 natural log of 2 times time. Okay. I would need this to make any sort of calculations about the future, any sort of predictions. The prediction it's asking us to make is to figure out how many bacteria could be present at the end of 96 minutes. So we're going to plug in 96 for T. If we were looking for an exact answer, we would only really be able to replace T with 96, and we would leave it like that. That's our exact answer. We'd need a calculator in order to get the rounded answer. Punching that into a calculator, you would get an approximation of 602,248.76 bacterium.